Good morning, Sir Joseph Tolentino. My name is Kian Opson of Group 6. This is our discussion for the topic Predicting Scores. The topics that will be tackled are simple linear regression, simple logistic regression, and multiple linear regression.
Hi, this is Bianca Marie Sanisa. I'm will talk about simple linear regression. Simple linear regression is a statistical approach for describing and investigating relationships between two continuous quantitative variables. One variable, denoted x, is regarded as the predictor, exploratory, or independent variable. The other variable, denoted y, is regarded as the response, outcome, or dependent variable. You can use simple linear regression when you want to know how strong the relationship is between two variables. Like for the example, the relationship between rainfall and soil erosion. The next is the value of the dependent variable at a certain value of the independent variable. Example of this is the amount of soil erosion at a certain level of rainfall. Simple linear regression models describe the relationship between variables by fitting a line to the observed data. Linear regression models use a straight line, while logistic and nonlinear regression models use a curved line. Regression allows you to estimate how a dependent variable changes as the independent variable or variables change. The simple linear regression models assumes that y sub I equals to beta sub 0 plus beta sub 1 times x sub I plus u sub I, where the y sub I is the represent the value of the dependent variable for the ith observation. The x sub I is represents the value of the independent variable for the ith observation. U sub I represents the error for the ith observation, which will assume to be normal u sub I, and parenthesis 0 sigma b sub the beta sub 0 and the beta sub 1 are the regression coefficients. Beta sub 0 is the intercept, while the beta sub 1 is the slope. Deterministic relationship. A deterministic or functional relationship is an exact relationship between the predictor x and the response y. Here are the example of deterministic relationship. Note that the observed x, y data points fall directly on a line. As you may remember, the relation between degrees Fahrenheit and degrees Celsius is known to be F equals to 95 Celsius plus 32. That is, if you know the temperature in degrees Celsius, you can use this equation to determine that the temperature in degrees Fahrenheit exactly. There are more examples of deterministic relationship like the Hooke's law, the Ohm's law, and the Boyle's law. Let's go to the statistical relationship. A statistical relationship, on the other hand, is not an exact relationship. It is instead a relationship in which trend exists between the predictor X and the response Y, but there is also some scatter. Here are the example of statistical relationship. The response variable Y is mortality due to skin cancer, number of deaths per 10 million people, and the predictor variable X is the latitude, degree north, at the center of each of 39 states in the US. The data were compiled in 1950s, so Alaska and Hawaii were not yet states, and Washington DC is included in data set even though it is technically a state. So there is the table of the skincare mortality versus state latitude. You might anticipate that if you live in the higher latitude of the northern US, the less exposed should be you be to the harmful rays of the sun, and therefore the less risk you'd have of death due to skin cancer. The scatter plot supports such a hypothesis. There appears to be a negative linear relationship between latitude and mortality due to skin cancer, but the relationship is not perfect. Indeed, the plot exhibits some trend, but it also exhibits some scatter. Therefore, it is statistical relationship, not a deterministic one. A linear regression model follows a very particular form. In statistics, a regression model is linear when all terms in the model are one of the following: the constant, a parameter multiplied by an independent variable. Then you build the equation by only adding the terms together. Dependent variable equals to constant plus parameter. When the function f of x is linear, this is the equation f of x equals to beta sub 0 plus beta sub 1 times x sub 1. If beta sub 1 is greater than 0, then there is a positive linear relationship. While beta sub 1 is less than 0, there is a negative linear relationship. So let's move on to nonlinear regression equation. If it is simple, if a regression equation doesn't follow the rules for a linear model, then it must be a nonlinear model. If the function f of x is nonlinear, like the example of f of x equals to log x, or f of x equals to x squared plus 3. So here are the example of nonlinear. That data that shows non-linear patterns.
Welcome to our first video on simple linear regression. In this video, we will discuss the two main objectives of simple linear regression, and also we're going to run an example that will help us start understanding how should we interpret the coefficients of a simple linear regression model. Simple linear regression, or regression models in general, have two main objectives. The first one is going to be to establish if there is a relationship between two variables. We're going to be talking about a positive relationship between two variables if they tend to move together, in the sense that when one increases, the other one increases as well. And conversely, in a negative relationship, we find that if one variable's values increase, the other variable's values tend to decrease. More specifically, we're going to be talking about statistically significant relationships between the two variables, but we will get back to this later. Let's talk about some examples. On average, we expect that people or families that earn higher income will generally spend more of a given product. In this case, we're talking about a positive relationship between income and spending. We could also analyze and test if there's a relationship between wage and gender. We could ask if men are more likely to earn higher wages than women, case in which we're talking about gender discrimination, which is negative and we don't want it, but we can actually use the regression models to test if that relationship exists. Another example that I hope you find odd is relationship between a student's height and that same student's exam scores. We should expect no relationship to exist, and we can use our regression models to test that. Our second objective is going to be to forecast new observations. And what we mean here is, can we use what we know about an existing relationship to forecast unobserved values? Let me give you a couple of examples. For instance, if we know that our sales tend to grow over time, and we actually even know how strong this relationship is, and we know how fast our sales grow, we could use this information to predict or to forecast what will our sales be over the next quarter. Also, if we have data on stores and we know how profitable different stores are, and we know what is the relationship between how much competition a store is facing in a given location, or what the population of a location is and how those variables impact the store's profitability, we could use what we know about previous stores to evaluate the profitability of a new inexistent store. Of course, we don't know how profitable the new store is going to be, but if we know how much competition it's going to face and we know how much people live nearby the store, then we can use this information to forecast that store's profitability. In general, we're going to be talking about two different roles that variables play in regression models. The first one is going to be the dependent variable. This is the variable whose values we want to explain or forecast. And we call it the dependent variable because its values depend on something else, and we will be denoting it as y. The other role is that of the independent variable, and this is the variable that explains the other one, and we say that its values are independent, hence its name. We will denote this value as x, or this variable as x. When we use simple linear regression models, we call them linear because the magic is that we're using a linear equation. And from your high school years, you might remember one of these, where y is a function of x, and there's a term that is added to the function and another one that multiplies the x. In the stats world, we like Greek letters, and we're going to be using a slightly different notation. Our linear equation is going to have a beta 0 term, which we're going to be calling the intercept or the constant, and the beta 1, which is the term that multiplies the x, and we're going to be calling the coefficient of x or the slope of x. And as a recap, we call these linear equations because they will appear as a straight line if we plot them in a b-dimensional plot. Let me show you an example of a linear equation. And remember, our model is y equals beta sub 0 plus beta 1 times x. And let's simply give numbers to those betas. And let's say that we have a linear equation y equals 4 plus 2x. Let's analyze what the 4 means. 4 is the distance from the horizontal axis at which the line crosses the vertical axis. In this case, if x had a value of 0, y equals 4. And we see here that the line is crossing the vertical axis 4 units above the horizontal axis. The slope in this case is a 2. And it means that for every unit increase of x, y will increase twice as much, or 2 times as much. We see here that x increased from 2 to 4, while y increased from 8 to 12, twice as much. Let's further understand this and wonder what happens if we change the intercept. In particular, let's use a larger intercept. Let's change the intercept to a 9. We see that we're moving the line upwards, meaning that we're increasing the distance from the horizontal axis to the point where the line intersects the vertical axis. We could also have a negative intercept, which would imply that the line is intersecting the vertical axis below the horizontal axis at a negative number. If x were 0 here, y is minus 2. Now, what happens if we change the slope? If we change the slope, we're changing the sensitivity of y on values of x, meaning how fast or how slow y will change when a unit of x is changed. If the slope were a 5, that means for every unit of x, y is going to increase 5 times. So you see that we have a much steeper slope because y is growing much faster than it was before when we had a 2. What would happen if we had a 0 slope? This would mean that it doesn't matter what value x has, y will always be 4. And if we go all the way around to a negative slope, a minus 3 in this case, we have a downward slope, and this represents that y will decrease 3 units for every unit of x. Now, in this case, we're talking about very crisp and clear straight lines, but data in the real world does not behave like this. Data in general is going to be a series of x and y observations that on average may follow a linear pattern, and that's why we use linear regression models to represent them. But the line is not always, and actually most generally, not intersecting or passing across any of these dots. Rather, there are going to be errors that we can measure, which are the distance between the dots in the real life and the actual linear regression. And what linear regression is going to do is trying to draw a line that minimizes these errors. But the important aspect we're going to take away now from this is that our linear regression model must include this error into it. So this is how our linear regression model looks like. It is y equals beta 0 plus beta 1 times x plus the error term. So let's recap. Y is the dependent variable, the variable whose value depends on all other parameters in the equation. X is the independent variable that helps explain the variance in the y. Beta 0 is our constant term or intercept. Meanwhile, beta 1 is the slope coefficient for the x. And epsilon, which is a Greek term to symbolize something that is very, very small, is going to be our error term, which we're trying to minimize. Now let's look at an example with actual data. We will try to explain a family's consumption of a given product. So think for the moment of any product. It could be cereal, it could be toys, it could be books. And try to wonder what determines a family's consumption of this product. And you may want to pause this video now and spend a couple of minutes thinking about what could you use to explain a family's consumption of a given product. Alright, maybe you thought about attributes such as how large the family is, and in general, larger families would necessarily have to consume more. But if you recall our early example, we talked about a positive relationship between income and consumption. And this is what we're going to have in the data we're going to use. Our data is going to be a series of 40 observations of 40 different families and their weekly income and consumption of a given product. So we have 3 columns in our data. The first one is going to be an observation ID, which generally has no meaning whatsoever. And the other 2 columns are going to be income and consumption. So how could we use these 2 columns in a simple linear regression model? Remember, our model has a dependent variable and an independent variable. And in this case, we're trying to explain consumption based on income data. So consumption is going to be our dependent variable and income is going to be our independent variable. And of course, the assumption we're making and what we want to test is if income is good enough variable to explain consumption. If we throw this into a statistical package, such as Gretel, this is what we observe. And for now, don't worry about all the numbers you see here. We will learn about them later. Focus on the coefficients, which are 2. And Gretel is indicating that our constant term is 49.1334 and that the coefficient for income is 0.852736. If we wrote this into our equation, we would find that consumption equal to 49.13 plus 0.85 times income plus the error term, which is going to be very important. Now, what do these numbers mean for our model which tried to see how did income explain consumption? Remember, our model is this one right here. Now let's start with 49.13. If income were 0, consumption would take this value, and consumption would be 49.13. So using this, we could interpret the intercept as the consumption level of a family with 0 income. Now this makes little sense unless we assume that there's a state-run program that offers financial aid to families with no income, such that thanks to this aid they can have some consumption, but more generally the intercept will not have an intuitive interpretation, meaning that in most cases we will actually be ignoring it. Now let's talk about the 0.85. This means that for every unit increase in income, consumption will grow by 0.85. We can call this the marginal effect, meaning that on the margin, income will grow 0.85 for every unit increase in income. And let's put some dollar numbers to this. Let's say a family's income is 100 more. So 100 times 0.85 means that for every $100 of income a family earns more per week in this case, the consumption will grow on average an expected of $85. Worth noting, the slope will always have an intuitive interpretation, which is the sensitivity of the dependent variable on changes in the values of the independent variable. And we will finish our example by showing the initial observations and the fitted linear model in the same plot. Here in this plot, the horizontal axis is income and the vertical axis is consumption. The 40 red dots you see represent each of the 40 observations of the families for which we had data on income and consumption. You can notice that they follow a growing trend, but they are not at all in a straight line. What we did, however, was draw a straight line that closest resembled the pattern followed by the dots. And this is the blue line, which shows the fitted values from our linear regression. What our estimation procedure did was try to draw a line that minimized the error between the red dots and the blue dots, but we will talk more about that later. This is all for this video. Thank you.
Good day everyone, so my name is Fatima Ira A. Mohammed and I am going to tackle about the simple logistic regression. So, what is simple logistic regression? Simple logistic regression, this is a statistical test used to predict a single binary variable using the other variable. This is also called as logic regression or binary logistic regression. Simple logistic regression determines the numerical relationship between two such variables. The goal is to estimate the probability of occurrence, not the value of the variable itself. So, logistic regression is analogous to linear regression. The only difference between both of them is that the logistic regression is used when the target variables is the relation, while linear regression is used when working with continuous target variable. Then, basically, the relation of logistic regression is used for classifying, whereas linear regression is used for regression. So, classifying the relation is the term used when a model is predicting the class and observation 2, while regression is associated with a model predicting the numerical value of a response variable. So, every statistical method has assumptions. Assumptions mean that your data must satisfy certain properties in order for statistical method results to be accurate. So, assumptions for simple logistic regression: linearity, no outliers, independence. Linearity. Logistic regressions assumes that the relationship between the natural log of these probabilities, when expressed as odds, and your predictor variable is linear. So, logistic regression fits a logistic curve to binary data. These logistic curves can be interpreted as the probability associated with each outcomes across independent variables value. And then next, the no outliers. Variables that you care about must not contain outliers. Logistic regression is sensitive to outliers or data points that have unusually large or small values. So, you can tell if your variables have outliers by plotting them and observing if any points are far from all other points. Then, independence. Each of your the data points should be independent. This means that each value of your variables doesn't depend on any of the others. This assumption is usually violated when there are multiple data points over time from the same unit of observation, because the data points from the same unit of observation are likely to be related or affect one another. Additional information: how the test works. Simple logistic regression finds the equation that best predicts the value of y variable for each value of the x variable. What makes logistic regression different from linear regression is that you do not measure the y variable directly. It is instead the probability of obtaining a particular value of a nominal variable. For example, the values of the nominal variable are spider percent and spider absent. The y variable used in logistic regression would then be the probability of spider being present on a beach. This probability could take values from 0 to 1. The limited range of this probability would present problems is used directly in a regression. So, the odds y over 1 minus y is used instead. If the probability of spiders on a beach is 0.25, the odds of having spiders are 0.25 over 1 minus 0.25 is equals to 1 over 3. In gobbling terms, this would be expressed as 3 to 1 odds against having spiders on a beach. Taking the natural log of the odds makes the variable more suitable for a regression. So the result of a logistic regression is an equation that looks like ln of y over 1 minus y equals a plus bx. You find the slope b and intercept a of the best fitting equation in a logistic regression using the maximum likelihood method rather than least squares method you use for linear regression. Maximum likelihood is a computer-intensive technique. The basic idea is that it finds the value of the parameters under which you would be most likely to get the observed results. For the spider example, the equation is ln of y over 1 minus y equals to negative 1.6476 plus 5.1215. So, rearranging to solve for y, the probability of spiders on a beach yields y equals to e raised to negative 1.6476 plus 5.1215 over 1 plus e raised to negative 1.6476 plus 5.1215, where e is the root of natural logs. So if you went to a beach and wanted to predict the probability that spiders would live there, you could measure the sand grain size, plug it into the equation, and get an estimate of y, the probability of spiders being on the beach. There are several different ways of estimating the p-value. The walled chi-square is fairly popular, but it may yield inaccurate results with small sample sizes. The likelihood ratio method may be better. It uses difference between the probability of obtaining the observed results under the logistic model and the probability of obtaining the observed results in a model with no relationship between the independent and dependent variables. I recommend you use the likelihood ratio method. Be sure to specify which method you've used when you report your results. So, some additional information on logistic regression. Models relationship between set of variables x, dichotomous, yes or no, categorical, social class, etc. Continuous, age, numbers, and so on. So, in continuous variables, increase in OR, or for continuous variables, increase in OR for a 1 unit change in exposure variable. Logistic model is multiplicative or increases exponentially with x. If R equals to 2 times 2 times 2 equals to 2 raised to 3, which equals to 8. So you can do a test in some apps or web. Spreadsheet. You can enter the data either in summarized form or non-summarized form. It uses the likelihood ratio method for calculating the p-value. The spreadsheet makes use of the solver tool in Excel. Web page. There's a very nice web page that will do logistic regression with the likelihood ratio chi-square. You can enter data either in summarized form or non-summarized form with the values separated by tabs, which you'll get if you copy and paste from a spreadsheet, or commas. R. Salvatore's Magnificus or Magnificus. Magnificus R companion has a simple R program for simple logistic regression. SAS use proc logistic for simple logistic regression. There are SAS use proc logistic. For simple logistic regression, there are two forms of the model statement. When you have multiple observations for each value of the measurement variable, each of the variable, your data set can have the measurement variable, the number of success. This can be either value of nominal variable and the total, which you may need to create a new variable for. Then last, power analysis. You can use G-power to estimate the sample size needed for a simple logistic regression. So when do we use simple logistic regression? We use simple logistic regression in the following scenario. First, you want to use one variable to a prediction of another, or you want to quantify the numerical relationship between two variables. Then second, the variable you want to predict is binary. Third or last, you have one independent variable or one variable that you are using as a predictor. So that's all about the simple logistic regression.
Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about logistic regression. This is a technique that can be used for traditional statistics as well as machine learning. So let's get right to it. Before we dive into logistic regression, let's take a step back and review linear regression. In another StatQuest, we talked about linear regression. We had some data, weight, and size. Then we fit a line to it. And with that line, we could do a lot of things. First, we could calculate R squared and determine if weight and size are correlated. Large values imply a large effect. And second, calculate a p-value to determine if the R squared value is statistically significant. And third, we could use the line to predict size given weight. If a new mouse has this weight, then this is the size that we predict from the weight. Although we didn't mention it at the time, using data to predict something falls under the category of machine learning. So plain old linear regression is a form of machine learning. We also talked a little bit about multiple regression. Now we are trying to predict size using weight and blood volume. Alternatively, we could say that we are trying to model size using weight and blood volume. Multiple regression did the same things that normal regression did. We calculated R squared, and we calculated the p-value, and we could predict size using weight and blood volume. And this makes multiple regression a slightly fancier machine learning method. We also talked about how we can use discrete measurements, like genotype, to predict size. If you're not familiar with the term genotype, don't freak out, it's no big deal. Just know that it refers to different types of mice. Lastly, we could compare models. So on the left side, we've got normal regression, using weight to predict size. And we can compare those predictions to the ones we get from multiple regression, where we're using weight and blood volume to predict size. Comparing the simple model to the complicated one tells us if we need to measure weight and blood volume to accurately predict size, or if we can get away with just weight. Now that we remember all the cool things we can do with linear regression, let's talk about logistic regression. Logistic regression is similar to linear regression, except logistic regression predicts whether something is true or false, instead of predicting something continuous like size. These mice are obese, and these mice are not. Also, instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. And that means that the curve tells you the probability that a mouse is obese based on its weight. If we weighed a very heavy mouse, there is a high probability that the new mouse is obese. If we weighed an intermediate mouse, then there is only a 50% chance that the mouse is obese. Lastly, there's only a small probability that a light mouse is obese. Although logistic regression tells the probability that a mouse is obese or not, it's usually used for classification. For example, if the probability a mouse is obese is greater than 50%, then we'll classify it as obese. Otherwise, we'll classify it as not obese. Just like with linear regression, we can make simple models. In this case, we can have obesity predicted by weight, or more complicated models. In this case, obesity is predicted by weight and genotype. In this case, obesity is predicted by weight and genotype and age. And lastly, obesity is predicted by weight, genotype, age, and astrological sign. In other words, just like linear regression, logistic regression can work with continuous data, like weight and age, and discrete data, like genotype and astrological sign. We can also test to see if each variable is useful for predicting obesity. However, unlike normal regression, we can't easily compare the complicated model to the simple model, and we'll talk more about why in a bit. Instead, we just test to see if a variable's effect on the prediction is significantly different from 0. If not, it means that the variable is not helping the prediction. Psst. We use Wald's test to figure this out. We'll talk about that in another StatQuest. In this case, the astrological sign is totes useless. That's statistical jargon for not helping. That means we can save time and space in our study by leaving it out. Logistic regression's ability to provide probabilities and classify new samples using continuous and discrete measurements makes it a popular machine learning method. One big difference between linear regression and logistic regression is how the line is fit to the data. With linear regression, we fit the line using least squares. In other words, we find the line that minimizes the sum of the squares of these residuals. We also use the residuals to calculate R² and to compare simple models to complicated models. Logistic regression doesn't have the same concept of a residual, so it can't use least squares and it can't calculate R². Instead, it uses something called maximum likelihood. There's a whole StatQuest on maximum likelihood, so see that for details, but in a nutshell, you pick a probability, scaled by weight, of observing an obese mouse, just like this curve. And you use that to calculate the likelihood of observing a non-obese mouse that weighs this much. And then you calculate the likelihood of observing this mouse. And you do that for all of the mice. And lastly, you multiply all of those likelihoods together. That's the likelihood of the data given this line. Then you shift the line and calculate a new likelihood of the data. And then shift the line and calculate the likelihood again. And again. Finally, the curve with the maximum value for the likelihood is selected. Bam! In summary, logistic regression can be used to classify samples, and it can use different types of data, like size and/or genotype, to do that classification. And it can also be used to assess what variables are useful for classifying samples, i.e., astrological sign is totes useless.
Hi, good day to each and everyone. My name is Yamar Cano and I'm going to be the third reporter of our group and discussing predicting scores, specifically multiple linear regression. So for this topic, we have come up with learning objectives, specifically 7 objectives, which is to articulate assumptions for multiple linear regression, explain the primary components of multiple linear regression. Third is identify and define the variables included in the regression equation. 4 is construct a multiple regression equation. Fifth is calculate a predicted value of a dependent variable using a multiple regression equation. 7 is to identify strategies to assess model fitting the equation, as well as, for last, interpret and report the results of multiple linear regression analysis, which is the goal of this topic. So, for the previous reviewer, we have discussed with simple linear regression as well simple logistic regression. So, for review, before going to my topic, which is multiple linear regression, review is that linear regression assumes a linear relationship between independent variables and dependent variable. Linear regression also allows us to predict an outcome based on one or several predictors. So it's like a one-to-one scenario or one-to-two scenario, one-to-many scenario, and depending on dependent and independent variable. So linear regression also allows us to explain the interrelationship among variables, and linear regression is a parametric test. So before in our discussion, we have to choose x and y, which are the variables in our topic. So y can be regressed on x. Also, x can be regressed on y, which means they have the relationship between each other and can be vice versa. So the regression is not symmetric. The choice of which regression to perform depends on the scientific question: is x to be used to explain or predict y, or is y to be used to explain or predict x? Example of this is that does poor health status explain high pollution level or otherwise? So another linear regression assumption is that independent variable can be any scale, ratio, nominal, interval, and many more. So dependent variable need to be a ratio or interval scale. But the mean by ratio is an quantitative variable which does not only make order but also makes the difference between the two between variables and can carry the true value of 0. Example of this is that instruments such surveys such as how many in a day can you eat burgers, when given with interval of 0, 1 to 2, 3 to 4, and with that the 0 has a true meaning with that, and it has an order and interval between the two. So interval scale also gives an order as well as makes the difference of between variables known. So dependent variable need to be normally distributed overall and normally distributed for each value of the independent variable. 4. If independent variable is not normally distributed, we can transform it, and we have image of normal distribution table. So the characteristic of a normal distribution table is that it has a bell curve. It forms a bell curve and it's symmetric between other sides, and the center is mean is equals to median is equals to mode. So we have this example transform data. Another assumption is that samples must be representative of the population. Samples should be gotten from the population or as a whole, so that we can get some alignment about our variables. So 6 is there is no multicollinearity. The independent variables are so strongly interconnected and they are indistinguishable from each other. Independent variable may given with situation like this in multiple linear regression, we deal with many independent variables, or it's like many is to one. One is like the dependent variable and many is the independent variable. And not independent variable correlates with the dependent variable, but also within the scope of independent variables, they also correlate within each other. So we should always assess about that before going to predicting scores or to give an analysis about our study. So we should check that they have connection. They do not have connection between other or otherwise. 7 is the relation between x and y must be linear. When two scores are graphed, they should tend to form a straight line, and that is not a linear relationship. Our methods must be used. So for every value of x, the distribution of y scores must have approximately equal variability or homoeisticity. So going with our topic, multiple linear regression. Given with a situation, what will you do if you are interested in studying a relationship between final grade with midterm or screening score and other variables such as previous undergraduate GPA, GRE score, and motivation? So with that, it involves a lot of variables, and a simple linear regression cannot handle this because it's like it's only deals with 1:1 scenario or otherwise, and a separate SLR which explanatory independent variable will provide information isolation. You will need to use a multiple linear regression with this, and with that MLR method we can study them together. So for the definition of multiple linear regression, a multiple linear regression model shows the relationship between a dependent variable and the multiple two or more independent variables. This is what I've been saying, that it deals with many independent variables, and we should always assess if there are relationship between them. So the overall variance explained by the model R2, as well as the unique contribution, strength, and direction of each independent can be obtained. And with that, in MLR, the shape is not really aligned. Yep, because it involves with many variables. If there are 3 variables, the shape is a plane. And if there are 4 or more variables, it is impossible to visualize the graph. However, by convention, we still refer to the regression equation as a regression line. So with this, we have an image of like many variables and multiple linear regression with 2 predictors. So with that, it's creating a plane between the variables. So going with the equation, the multiple linear regression equation, sometimes also called multivariate linear regression for MLR. The prediction equation is y equals to alpha plus b beta sub 1 x sub 1 plus b2 x sub 2 and so on, and there is still one intercept constant, which is a, but each independent variable, example x sub 1, x sub 2, and x sub 3 has their own regression coefficient. So in reviewing our simple linear regression discussion, y prime is a linear function of x and y prime is equal to a plus bx, where a is the intercept and b is the slope. So in our regression equation, we have this interpretation of multiple linear regression coefficient. Beta sub 1 is the expected change in y when x sub 1 increases 1 unit and x sub 2 remains fixed, or beta sub 1 is the difference between average y for 2 populations that differ in x sub 1 by 1 unit and have the same x2. So example of a regression equation. So y equals to b sub 0 plus b sub 1 multiplied by the age minus 40 plus b sub 2 gender plus etc. And salary is equals to 50 plus 1. So we have that age minus 40 plus minus 3 gender plus, and where salary is in $1,000, age in years, and gender equals 0 if male. For the interpretation of this is that y equals to b sub 0 plus beta sub 0 plus beta sub 1 multiplied by age minus 40 plus beta sub 2 gender plus the epsilon. So salary is equals to y and 50 plus 1 and age minus 40 minus 3 gender plus epsilon, where salary is in $1,000, age in years, and gender equals 0 equals if female and 1 if female. So for the interpretation, b sub 0, beta sub 0 is average salary in $1,000 for 40-year-old male, and beta sub 1 increase in average salary for every year of age for a given gender, MRF, and beta sub 2 is difference in average salary for women versus men of the same age. So interpretation is that continuation is what is the average salary for 50-year-old male. So average y is equal to 50 plus 1 times the 50 minus 40 minus 3 times 0 is equals to $60K. Another example of multiple linear regression equation is that interpret beta sub 0, beta sub 1, and beta sub 2 given with that data are from children aged 1 to 5 years in the variables is y is the child's arm circumference in centimeter, x sub 1 is the age of the child's months, x sub 2 is the height of the child in centimeter. With this, the arm circumference increase with increasing child's age after controlling for child height. So, with multiple linear regression, following the multiple linear regression model, we have y equals to b sub 0, beta sub 0 plus beta sub 1, x sub 1 plus beta sub 2, x sub 2. When we substitute, beta sub 0 is equal to the estimated mean arm circumference when the values of age and height are 0. And beta sub 1 is the change in the estimated mean arm circumference associated with each 1 month increase in age if height is unchanged. So B3 is equals to 0. Using the multiple linear regression, we can get 6 critical pieces of information from this. So the overall significance of the model, the variance in a dependent variable that comes from the set of independent variables in a model, the statistical significance of each individual independent variable controlling for the others, and the direct effect and the direction of the effect of each independent variable on the dependent variable, the relative strength of the independent variables, the regression equation which allow us to predict the values of the dependent variable given values of the independent variables. So the R squared, or the coefficient of determination. With this, it provides the proportion of variability explained by using X. And R squared measures the ability to predict an individual by using in excess. The statistical significance of the overall model, model F, test, and recall that R is a population correlation coefficient. Takes on values between -1 and +1. And 0 indicates no linear association, 1 indicates a perfect positive linear relationship, and -1 indicates a perfect negative linear relationship. So with this, we are given with example. We are interested in knowing the resonance frequently 5 or more times a week can lead to higher cholesterol. We also done at age, gender, and race or ethnicity can affect cholesterol. How can we tell if going out to restaurant frequently, this factor alone will affect cholesterol levels? So do age, gender, ethnicity, and going out to it frequently all affect cholesterol levels. So we are given with dependent variable cholesterol level, independent such as age in years, gender, male or female, race or ethnicity, black, white, Asian, or Hispanic. Frequency of going out to it is 5+ times a week versus less than 5 times a week. So linear regression assumption is that linear regression is a parametric method and requires the certain assumption be met to be valid. So the sample must be representative of the population, and that's the assumption. So the dependent variable must be of ratio interval scale and normally distributed and normally distributed for each value of the independent variables. The relation between x and y must be linear, and the independent variables are not very strongly interconnected or no multicollinearity. Using dummy variables is a way to express nominal independent variable with multiple categories. The number of dummy variables rated will be 1 less than the number of categories of the variable. One of the categories is chosen to serve as the reference for category. You can include all the dummy variables in the regression model instead of the original categorical variable. So, example is, let's say we have a race or ethnicity variable with 4 categories: non-Hispanic white, white non-Hispanic black, non-Hispanic Asian, and Hispanic. If we want to use it in a multiple regression, we would need to create 3 variables for 4 to 1 to represent 4 categories. We put this into the multiple regression equation instead of the 4 category race ethnicity variable. So this is like the representation for that, and with that we have the table and we can get information from this. So the overall variance explained by the model. Do the independent variable in the models taken together do a good job at predicting the dependent variable using the adjusted R-square. So statistical significance of the overall model, the strength, direction, and statistical significance of each independent variable. Regression equation as a whole can be used to predict values of the independent variable for a given set of values of the independent variables. So we have this analysis example. We will use data on 489 night change study participants to look at a number of potential predictors of total cholesterol. The independent variable is the total cholesterol, and we can see that total somewhat writes good from the image. It writes good table. And to correct for this departure from normally, an adjustment called a linear transformation of the variable can be made. In this case, we take the natural log of cholesterol. This makes the dependent variable normally distributed. From a while ago, its right skids, and now it is in a normally distributed variable. With this, we will use multivariate linear regression to look at a number of dependent variables. Gender, female, 1 versus male equals 0, age, content mass. Frequency of eating in restaurants, frequency 1 and frequent 0, and race, ethnicity, black, white, Asian, or Hispanic. Note that there has 4 categories in it. To look at this variable in regression, we will have to create dummy variables. So we have the analysis example or the model summary. Adjusted R squared is equals to 0.031, and the foreign explain 3.1% of the variance in the dependent variable. For analysis example ANOVA, the p-value for the overall model is 0.004. The amount of variance explained by the model is statistically significant, which is the model is statistically significant, or the independent variables are statistically significant to the dependent variable. And analysis example coefficient: beta for gender, beta for age, beta for eating restaurants, beta for black. Using the regression equation, beta for Asian and beta for Hispanic, the regression constant 5.189. So with this, we solve is that estimated equation. For the example prediction, from this model, we can predict that the total cholesterol of a 25-year-old white woman who does not eat often. So predicted in cholesterol equals 5.189 equals 0.0015, and we get 5.2629. So the cholesterol values were lag transform, so need to back transform, and don't forget about it. So example significance can look at significance of individual coefficient of overall model significance in ANOVA. From the p-values, we can see that the only age is significantly associated with total cholesterol. It means that the other independent variables are not associated with the cholesterol and does not affect the total cholesterol level. And the ages have higher significant association with the cholesterol level. And conclusion can be stated as follows. This model explains 3.1% of the variance in total cholesterol, and this is statistically significant at alpha 0.05. Age is positively associated with total cholesterol, such that adjusting for the other variables in the model for each additional year in age, the natural lag of total cholesterol is predicted to increase by 0.002 units, and this association is statistically significant. None of the other variables in the model were significantly associated with total cholesterol. So with that, before going to ASED, we should also check in the multicollinearity and MLR. The independent variables in the model are strongly associated with each other, that they are essentially measuring the same thing. We would like to see no or very small multicollinearity among the independent variables, and the tolerance of a variable is used as a measure of collinearity. To obtain measures of tolerance, the independent is treated as a dependent variable and is regressed on the other independent variables. Yes, with this, we have this checking assumption using red seed balls. Of course, in this analysis, it's important to have an approach for selecting variables. First, it is common to look at a correlation matrix or SLR models. And there are a number of approaches to choosing which variables to include in a multiple regression model. Standard approach or simultaneous method, all the independent variables are entered at once. Stepwise for backward or stepwise solution, the software selects the best model based on a series of steps in which variables are added and removed depending on their association with the outcome. Hierarchical, the researchers compares two or more models before and after the addition of certain variables of interest, and users present criteria for selecting the best model. So with that, to tackle all the discussion, we have a summary of this discussion, which is multiple linear regression can be used when the outcome of interest is of interval or ratio scale and normally distributed. The independent variables can be on any scale, but dummy variables need to be created for all polytomous, categorical, or nominal independent variables. And using the regression model, we can estimate the strength and direction of the association from the adjusted betas. We can also determine the statistical significance of each parameter in the model using the p-value or the 95% confidence interval around the beta. So that's all for today, and that's the last topic, which is the multiple linear regression for predicting scores.